In this section, we'll look in detail at some of the chemistry that can happen in liquids and liquid mixtures. We already know that to say something is a liquid, we're simply describing its physical state. As a physical state, liquids tend to have more molecular motion than solids, but less molecular motion than gases. We also know that liquids have a defined volume, but a variable shape. In other words, you can pour a liquid into different containers, and while it'll take the shape of those containers, you're always stuck with that particular volume or amount of space that the liquid takes up. In chemistry, when we say the word liquid, we're usually referring to something that is a pure substance. For instance, liquid water. Liquid water is actually referring to pure H2O. In a sample of pure water, we would have nothing but H2O molecules. There are only a limited number of substances that actually exist as pure liquids at room temperature. Another example is something called octane. Octane is an example of a hydrocarbon, meaning it's made entirely of carbon and hydrogen atoms. Octane has the chemical formula C8H18, and it's a sort of a yellowish liquid at room temperature. It contains nothing but C8H18 if it's truly pure octane. Hydrocarbons are one of the few substances that's naturally a liquid at room temperature. However, you can probably think of many liquids that you come in contact with in your day-to-day life. The reality, however, is that these aren't actually pure liquids. Most of the substances around us that appear as liquid are actually mixtures, meaning they consist of more than one chemical species or more than one type of molecule. For example, even the water that comes out of your tap isn't pure water. As you probably already know, tap water and purified and bottled water as well contain many naturally occurring substances, such as ions like calcium, magnesium, and bicarbonate. So even the water that we think of as being a liquid is actually a type of mixture. This is true for most of the things that we drink, whether it's water, something like orange juice, which is a mixture of water, sugar, vitamin C, and many other substances, or soda, which is a mixture of water, sugar, acid, and carbon dioxide. Other substances that we think of as liquids are also mixtures. The blood that courses through your arteries and veins is a very complex mixture. It contains all sorts of different substances. Synovial fluid, which is another type of liquid within your body in your joints. Even liquids outside of our bodies, such as rainfall or the water in rivers, lakes, and the ocean, generally tend to be mixtures. So while all these different substances act like liquids, they actually fall into the category of mixtures. There are actually two categories or two classes of mixtures: homogeneous mixtures and heterogeneous mixtures. As you can probably guess from the prefix, what this has to do with is whether they look the same or whether they look different when they're mixed. A classic example of a heterogeneous mixture is oil and vinegar. If you've ever mixed oil and vinegar together, you know they essentially don't mix. In other words, when you put them together and you shake them up, they still separate into their separate components. This is what we call a heterogeneous mixture, because it clearly looks different throughout. Within the classes of homogeneous mixtures, there's actually two separate categories. One is what are called colloids. Colloids are homogeneous, meaning they look the same throughout. However, because of what's happening at a molecular level, they don't allow light to pass through them. As a result, colloids appear to be opaque, meaning you can't see through them. Some examples of colloids are orange juice, milk, and Pepto-Bismol. These are all substances that appear to be liquid, but in reality they actually are mixtures of different components, and we can't see through them. The other category of homogeneous mixture is what are called solutions. Solutions are also homogeneous, but the difference between a solution and a colloid is that a colloid is opaque, while a solution is clear, meaning you can see through it. Classic examples of solutions include things like salt water, tea, lemonade, and cranberry juice. Notice that they don't necessarily have to be colorless, only clear, meaning that you can see through them. We're going to take some time now to look at solutions in more detail, and that's because they're actually interesting on a molecular level. Think about it. When you mix something like salt and water together, it's almost as if that salt has disappeared. We know from what we've learned previously that salts often dissociate, but even covalent compounds like sugar often disappear when you mix them with water. So what's happening that allows some substances to basically disappear to the naked eye when mixed with liquid, while other substances, like oil and vinegar, still stay separate? Let's look at some of the chemistry about what's going on. The reason that solutions form has to do with those intermolecular forces. Let's look at a simple example. Most of the human body is comprised of things that are dissolved in water. And because of that reason, we run into aqueous solutions a lot in biosciences. And of course, to be a solution, they have to dissolve into that to the point where we can't see them. When you think about a sample of water, even before anything's dissolved in it, we know that there's already several different intermolecular forces at play. Water, like all substances, has London dispersion forces, which are the weakest of the intermolecular forces. Water is polar, so it also has dipole-dipole interactions, or dipole-dipole forces. And the strongest of the intermolecular forces that water has is the hydrogen bonding intermolecular force. These are the forces that are keeping the liquid molecules together. And as we studied, it's the reason that it takes a lot of energy, or in other words, a lot of heat, to cause water to boil. The reason, however, that things will dissolve in water also relates to these intermolecular forces. If I want to take this water and mix something into it, I will no longer have the pure substance, H2O. Instead, if it does mix and we do get a homogeneous clear solution, I'll have an aqueous solution. As soon as I have an aqueous solution, we change the names of the things we're working with. So for instance, water, when it's pure, is a liquid. But when we're talking about an aqueous solution, meaning one thing dissolved in another, instead of referring to a liquid, we refer to the solvent. The solvent is always a liquid with something dissolved in it. The thing that we dissolve into the solvent is what's called the solute. What's interesting about this is solvents always, by definition, have to be liquids, but solutes can be solids, liquids, or gases. So a solute could be a solid, like salt. We'll run into a lot of solid solutes. A solute could also be a liquid. An example of a liquid would be something like vinegar or alcohol that's dissolved into water. An example of a gas dissolved in water is something like oxygen or carbon dioxide that has dissolved in water. All of those could be considered solutes as long as they dissolve to give us a homogeneous, clear mixture, better known as a solution. So why does a solute dissolve in a solution? Well, it'll only happen if you drop that solute into the solvent, in this case water, and the solute and the solvent become attracted to each other. So in this way, it's a lot like other things we've seen where we need to have attraction between the different species involved in order to get anything to occur. For a solute to dissolve in a solvent, the solute and the solvent have to be attracted to each other. If they're not attracted to each other, we'll actually get two different physical layers that form. And you may have seen this, like when you see oil and water not mixing together. How are solutes and solvents attracted to each other? Well, they're attracted to each other through the same intermolecular forces that attract pure liquids to each other. We'll see that if you look at the intermolecular forces of your solvent and you compare them to the intermolecular forces of the solute, if they're similar, most likely the solute will dissolve. If they're not similar, most likely the solute will not dissolve. So what does it mean to say that they're similar? Well, molecules with similar intermolecular forces doesn't mean they have to have identical intermolecular forces, but they do have to have at least some way they can interact with each other. Molecules that do have similar intermolecular forces will attract and therefore dissolve each other most oftenly. This is often called the like dissolves like rule, meaning like intermolecular forces dissolve other molecules with like intermolecular forces. I usually think of this as two major categories. The first category are molecules that can hydrogen bond or are polar or have an ionic charge. So if you come up with two different molecules and you want to know if one will dissolve into the other, there's a good chance they'll dissolve into each other if one can hydrogen bond and the other can either hydrogen bond or it's polar or it has a charge. And you can take any two combinations. So a hydrogen bonding solvent will easily dissolve a hydrogen bonding solute, or a polar solvent will often dissolve an ionic solute. The other side to this understanding is that molecules that are not hydrogen bonding and not polar and not ionically charged often only dissolve in each other. These very typically are molecules that only have London dispersion forces. And in between, there's very little mixing. So if you take a solute that has hydrogen bonding interactions and you try to dissolve it in a solvent that's a non-polar liquid, it's very unlikely the two of them will combine to any appreciable extent. In fact, that's a good case where you're likely to get two separate physical layers of solvent and solute. Now, in this case, let's do some practice picking out molecules that can dissolve in each other. Which of these two substances are likely to be miscible, meaning dissolve into each other? I'll give you three different substances. The first one is water, or H2O, which we all know the chemical structure of pretty much by memory at this point. The second is something called acetic acid. We've run into acetic acid in the lab before, but if you don't remember it, I'll hold off on reminding you what it is until we're done with this exercise. The chemical structure of acetic acid is a carbon double bond to an oxygen that's also single bonded to an oxygen and then a hydrogen. On the other side of the carbon is a CH3, or a methyl group. And my final molecule is octane. This is a molecule that has 8 carbon atoms in a line all together. So there's 1, 2, 3, 4, 5, 6, 7, and 8 carbons. And octane has nothing but hydrogen atoms around those carbons. So if you want to write in all of your hydrogens, it'll look like this. Now, you have water, acetic acid, and octane. 2 of the 3 of these will mix together. See if you can explain which ones will mix together or which ones will be miscible with each other and why based on intermolecular forces. So your first step is really to look at the intermolecular forces. Pause the video and give it a try. Alright, as I look at my intermolecular forces, I know that the strongest intermolecular force affecting water is hydrogen bonding, and it also has dipole-dipole and London dispersion, but for these we often only need to know the strongest force. I'll write down the other two just in case. So dipole-dipole and London dispersion for water. Now I'm going to look at acetic acid. Again, I just want to figure out, first of all, I know it has to have London dispersion because it exists and all molecules have London dispersion. Second of all, I need to look at if it's polar or nonpolar. I see 2 oxygens. My gut tells me that those oxygens are pulling electrons towards them. So I probably have a vector arrow, something like that. In any case, I'm not convinced that all those oxygens are canceling each other out, so I'm definitely going to call this polar and therefore give it dipole-dipole. And second, and most important, I'm going to notice that it has a hydrogen bonded to an oxygen. Hydrogen bonded to N, O, or F, as long as that N, O, or F has electron pairs on it, makes it able to hydrogen bond. So this will also do hydrogen bonding. My last molecule is octane, and as you might even remember from lab, octane has nothing but carbon-carbon and carbon-hydrogen bonds, so like all hydrocarbon molecules, it has nothing but London dispersion interactions, and that's because it's guaranteed to be a nonpolar molecule. Now that I look at these 3 molecules and their intermolecular forces, I can see that the 2 that have similar intermolecular forces are water and acetic acid. Acetic acid can hydrogen bond, and so can water. So these two molecules will be miscible, or in other words, will dissolve into each other. Now I'll remind you that acetic acid is really the active ingredient, or the thing that makes vinegar smell and taste like vinegar. And vinegar, the way you buy it from a store, is dissolved in water. Octane, on the other hand, is a component of gasoline. And if you've ever been to a gas station after the rain, you know that gasoline and water don't mix, because you've probably seen puddles of water with gas floating on top. It's the same reason oil and water don't mix. We know that the entire reason comes from the intermolecular forces. And remember, you don't have to have identical intermolecular forces, they just have to be similar. So if we had a compound that only had dipole-dipole and London dispersion, that would still mix better with the water than it would with the octane. This is how you predict whether two substances will be miscible or soluble in each other. And it's how we recognize when a solution is going to form as opposed to when something like a heterogeneous mixture is going to form. That solubility of a solute in a solvent is highly predictable based on what we just saw, which is commonly referred to as the like dissolves like rule. So again, just by figuring out what intermolecular forces are in play, we can figure out which compounds are likely to be miscible with each other. We can, however, to a small extent, manipulate how well different solutes dissolve in their solvents. So we can manipulate some conditions that, while they won't completely change our like dissolves like rule, they can somewhat increase or decrease the solubility of a solute in a solvent. How much they do this and whether it works at all really depends on the physical state of the solute involved and the changes that you make. The two main changes, or the two main ways you can manipulate the solubility, meaning if you want something to dissolve in a solvent and it's not doing it on its own, is by changing temperatures and pressures of your system. Let's look first at manipulating the solubility of gases that dissolve in a solvent. To manipulate the solubility of a gas, maybe you want to get carbon dioxide or oxygen to better dissolve in water. One of the things you can do is change the temperature of that solution. Changing the temperature has a pretty significant effect on how much and how well the gas will dissolve. Here's a chart from your book that shows the solubility, or how well the gas dissolves, based on temperature. On the left side of the graph, we can see temperatures that are relatively cold, and that's compared with the right side of the graph, which shows temperatures that are pretty hot. You'll notice that the general trend of the gases on this graph is to get less soluble, or to have solubility that decreases with the temperature. And in fact, this is exactly what happens with most gases. To one extent or another, the higher the temperature, the less of the gas will actually dissolve. Or as we say, as temperature increases, solubility decreases. This is one of the reasons that you probably know you're not supposed to leave that goldfish that you win at the fair on a hot, sunny window, because eventually the goldfish will get very unhappy, have trouble breathing, and potentially even pass away. The reason is, as we go to higher and higher temperatures, gases like oxygen don't dissolve as well into the solvent water. So while oxygen may be at significant amounts at room temperature in that water, as the water warms up, less and less of the gas can stay dissolved. This is even more true with carbon dioxide. Carbon dioxide, which is the orange line on this graph, decreases to an even more significant extent. And this is why warm soda or warm beverages tend to have less carbonation than their colder counterparts. The colder a solvent is, the more it can dissolve of a gas. So as temperature increases, solubility actually goes down, meaning you can dissolve less and less of that gas. The other way you can manipulate the solubility of a gas is by changing the pressure on that gas. When you change the pressure on a gas, it has a very different effect than changing the temperature. For instance, if I take a gas and I subject it to very, very high pressures over a liquid, I can actually get more of that gas to dissolve. So at high pressures, we actually get high solubility, or high amounts of the gas dissolving. One way we can see this is by looking at how commercial soda manufacturers carbonate their drinks. If Coca-Cola wants to produce carbonated Coca-Cola, one of the things they can do is put carbon dioxide gas into the can and then close the can under very, very high pressures. What this does is essentially forces that carbon dioxide into the can and into the liquid in that can. And that's why the gas actually dissolves. It's not sitting on a layer on top of the liquid, it's actually dissolved in the liquid. We see this effect when we release the pressure by opening the can. When you open the can and pour it out, you now have a lower pressure. At the lower pressure, much of that carbon dioxide can't stay dissolved. It has a lower solubility. Because less can stay dissolved, we see the carbon dioxide start to bubble out or come out of the solution. And so this is why when you open a can of soda, it's not as if there's a layer of carbon dioxide sitting on top of the can. It's actually carbon dioxide that was dissolved in the liquid that begins to come out of the liquid. And as you leave it sitting at room temperature, you can see those bubbles coming out of the liquid until eventually the soda goes completely flat. So the relationship here is different than the relationship with temperature, because as pressure increases, solubility actually increases. So at high pressures, you get more gases dissolved in liquid. This is also a problem for people that scuba dive, because our blood is basically an aqueous system. And as you go to high pressures at very, very deep levels under the ocean, you can get gases dissolving in your blood that are not naturally there. If you come to the surface of the ocean too quickly, that releases the pressure and the gases can't stay dissolved. They literally bubble out of your blood the same way that gas bubbles bubble out of Coca-Cola when you open the can. Obviously, that's a bad thing. It's something that's called the bends in diving, and it can be fatal if it's not treated immediately. So in all situations, as pressure increases, your solubility increases. You get more gas dissolved. If you decrease pressure, the gas will come out of solution. You'll have less gas dissolved. You can also manipulate the solubility of solids and liquids, but the relationship is a bit more complex. For instance, if you manipulate the temperature of a liquid and you watch how the solubility of a solid or a liquid, it changes as a result, you'll see a variety of different effects. Many substances do become more soluble at higher temperatures, and you can actually remember this just by the simple fact that you've probably noticed that salt and sugar both dissolve better in hot water than they do in cold water. That's not always the case though. There are plenty of examples of compounds that either don't change very much or actually decrease in solubility as temperatures warm up. So generally, if you were a betting person, I would bet that a substance is going to dissolve more at higher temperatures, but it's not guaranteed, and we actually have to check how it is for each individual substance. Same thing with pressure, although there's actually no effect whatsoever. So if you'd like solids and liquids to dissolve more than like dissolves like tells us they will, you're kind of on your own. Maybe heating that liquid up, heating that solvent up will allow more to dissolve, but it might not. And if you increase the pressure on that solvent, it won't have any effect. For instance, if you increase the pressure on salt water, it doesn't make any more salt dissolve. All different types of solutions are simply comprised of a solvent with something dissolved in it, which we call a solute. And you could have many different solutes. So in your bloodstream, there are many different things dissolved in the water of your bloodstream. In ocean water, there are many different types of gases as well as liquids and solids, including salt, dissolved in that water. All of them, however, can be measured to have a certain concentration. When we think about the word concentration, right away we have an ability to understand what it is. Let's say you're at a restaurant and the waiter brings you some soup and you taste it and think the soup is much too salty. Right away you know that if you want to fix that soup, aside from sending it back, you could add some water to the soup and that would make it less salty. You know that you can't just get a smaller cup of the soup because it'll still have the same amount of salt per every spoonful that you put in your mouth. So we have an idea of concentration even before we get into the numbers of it. Another example is you might have very strong or very weak coffee. And in that case, you might be talking about the amount of caffeine in the coffee or the amount of the other flavors that you can taste. And again, you know that just having a bigger or a smaller glass won't change the taste, although it will change the amounts that you're exposed to. And while all those examples make things more or less pleasant for us, salty soup or caffeinated coffee, there are really important examples, like how much potassium is dissolved in a patient's IV drip. In that case, it's not just the amount of potassium they're getting, but it's how much liquid we have to give them to get them that amount of potassium. So concentration in a nutshell really comes down to how much stuff or how much solute you have and how much liquid or how much solvent you dissolved it into. If you don't know one of the two of these, you can't know the concentration. The downside to this very open-ended definition of concentration is, as you can imagine, you can put many different units on concentration. So you can measure how much stuff in terms of molecules or pounds or milliliters or virtually anything else. And same with liquid. You can measure liquid in many different ways. There are several units of concentration, however, that are the kind you're most likely to run into. So we'll just look at a few of them now. Probably the most common unit of concentration in chemistry is the unit of molarity. And as you can imagine, this relates to moles. The reason this is so useful is, as we've seen, any chemical equation requires us to relate the different molecules in terms of moles, or the stoichiometry of that equation. So by having a unit that works with moles, it allows us to skip a lot of steps doing conversions with things like concentration and molecular weight. Molarity itself is defined as the number of moles that are in 1 liter. We abbreviate molarity with a large capital M. And it's really easy to calculate as long as you know how many moles you're working with and how many liters you're working with. If you wanted to calculate the molarity of a substance that has 2 moles in 1 liter, maybe it's 2 moles of salt or 2 moles of sugar dissolved in 1 liter of water, I can find that simply by calculating that the molarity is 2 moles divided by 1 liter. So my final molarity would be 2 with the unit capital M. That capital M, even though it's molarity, is pronounced molar, like your tooth. So we would say that if you put 2 moles in 1 liter of water, you have a concentration of 2 molar. You can do the same calculation even if you don't have exactly 1 liter of water. For instance, if you dissolved 4 moles of a compound into 2 liters of water, your molarity would be 4 moles divided by 2 liters, and that still gives me a total of 2 molar. So even though we define molarity as the number of moles per 1 liter, if you're calculating it, it's okay to use any number of liters you want on the bottom. Just make sure you are in liters. The only time you don't want to do that is when you're using molarity as a conversion factor. Because it's a complex unit, the number of moles per liter, be sure to take advantage of the fact that that capital M really can be converted into a conversion factor. For instance, if you find out that you're working with a substance that has a concentration of 3.86 molar NaCl, that really means that there's 3.86 moles of NaCl per 1 liter of solvent. Because this is an aqueous solution, that solvent would be water. So I can rewrite this as a conversion factor by saying that there's 3.86 moles in 1 liter, specifically 1 liter of water. Notice that that capital M can be converted into 2 units at once. And so you could use this as a conversion factor in this form or flip it upside down and use it that way as long as you make your units cancel. Molarity is really easy to work with because it's just moles and liters, but often there are other units of concentration that you'll run into in different contexts. If we're dealing with compounds or species, or especially substances where we don't need to be as specific about the chemistry, we'll often run into the percent concentration. There are really, strictly speaking, different types of percent concentrations, such as the weight volume percent, or WV percent, Weight volume percent allows us to not have to work with the concept of moles, so it's often used when we have many different chemicals mixed together. It's also used in contexts where the science isn't quite as important. So weight volume percent is just defined as the mass of the solute in grams divided by the volume of the solution in milliliters multiplied times 100 to turn it into a percent. For instance, medical saline solutions are very carefully controlled and well understood, but they do contain a lot of different ions. Because of that, their concentration is often just expressed as a weight volume percent. Medical saline solutions are typically prepared by adding 9 grams of the salt mixture to 1 liter of water. Take a second and see if you can correctly calculate the percentage of 9 grams of salt per 1 liter. The weight volume percent here, I would just follow the example. I have a mass of my solute, which is 9 grams, and the volume of my solution is 1 liter. Notice, however, it's very important that our units are in grams on the top and milliliters on the bottom. So in order to use weight volume percent, I need to change that 1 liter into milliliters. In this case, I would have 1,000 milliliters because I know there's 1,000 milliliters in a liter. And then I'll multiply by 100 to get my percentage. So 9 divided by 1,000 times 100 gives me a weight volume percent of 0.9. That 0.9 means that there is less than 1% salt for the water that it's been added to. So you'll run into weight volume percents occasionally, and if you're dealing with a solute that's not a solid, such as a liquid, you'll often run into volume percents. Alcoholic beverages, if you check your container next time you're in a grocery store, things like wine and beer are labeled with a volume percent. It's the milliliters of the solute, which in that case would be ethanol or alcohol, over the milliliters of solution, which is water in that case. So the volume percent often shows up as well. There are still other units of concentration that we'll work with, although you're more likely to just see these than to actually have to do math with them. One example is the parts per type of unit. We run into parts per units often when we're working with substances in very, very low concentrations. So if you're dealing with a substance that you're medicating somebody with, you're more likely to see a concentration there in terms of percent or molarity or other units that we'll encounter later in this chapter. But if we're dealing with something like an environmental toxic agent, we might have a very low concentration that's still important for us to know. That unit might be given in parts per million, parts per billion, or you can even see parts per trillion. There's also parts per thousand, and you can really use any unit you want. For example, even though we would never give a medication in terms of parts per million or parts per billion, the EPA, or the Environmental Protection Agency, requires drinking water to be less than 10 parts per billion of arsenic in order to be deemed safe to drink. To give some perspective to that, that means that there would be 10 parts of arsenic per billion parts drinking water. And you can see it's a little bit more vague, because does that mean 10 molecules of arsenic for a billion molecules of water? Or could we measure that as 10 grams of arsenic for a billion grams of water? Because there's a lot of vagueness about this type of a calculation, we won't be using it in calculations. We'll only be using it just to generally understand what it is. And like I said, it's usually used with really low concentrations. In fact, lower than you might even be able to appreciate. There's a fantastic website called the Penny Project that allows us to see just how big parts per million or parts per billion is. For example, if this is a gentleman who's about 5'9" and these are stacks of pennies, what you're looking at are 1 million pennies all stacked together. Now, 10 parts per billion arsenic would mean that there would be 10 molecules of arsenic per billion molecules of water. And here's what a billion pennies looks like. It's 5 school bus size containers, essentially, of pennies. So 10 parts per billion arsenic means you could go in, and if each of those pennies represents a water molecule, you can replace just 10 of them with arsenic molecules and still have drinking water that's considered safe to drink. When dealing with concentration, very often we find ourselves diluting those concentrations by adding additional liquid. And dilutions are another concept that you probably already understand pretty well already. The idea is you start with a solution. Because it's a solution, we know it has a certain concentration of solute, and it may have more than one solute, but that certain concentration we can call C1, and it has a certain volume initially, which we can call V1. If I'm going to dilute this, the same way that you dilute concentrated orange juice, or you can dilute a concentrated patient medication, you can dilute it, and when you do that, you get two effects. First of all, we would expect that our volume went up. So my V2, or my second volume, is going to be higher than the first one. And as a result, my concentration after I've done the dilution, or in other words, my C2, is actually going to be lower. So it increases the volume while lowering the concentration. What about if you know what concentration you want to end with, and you want to figure out what volume do you need to add? Well, to do that, you can use a simple calculation called C1V1 equals C2V2. In this case, your first concentration and your first volume are C1 and V1, and your second concentration and your second volume are C2 and V2. Notice this V2 is your total final volume. So it's not the amount you add, it's you add until you have this total final volume. The reason is, it's not quite as clear as you might think that if you need to double the volume, you add twice as much liquid. In fact, different intermolecular interactions can affect that. Let's look at an example. Very often in medical science, as well as laboratory science, you'll need to use what are called stock solutions. A stock solution is essentially what you have in your stock room, and often it's a series of bottles that have a concentrated liquid in them. It's very similar to when you buy concentrated juice at the store with the intention of diluting it down to something you can use at home. The reason we have concentrated stock solutions is it just takes less money to ship them around than it would to have the final solution. It also gives us more flexibility because we can dilute these to any concentration we want. Let's say that initially you have a 6 molar stock solution in your stock room, and you're asked to prepare 500 milliliters of a 3.0 molar solution. In order to do that, you can simply use the C1V1 equals C2V2 calculation in order to determine how much of your stock solution you actually need. So take a second and see if you can figure out how much stock solution you would need to dilute in order to get a total ending solution of 500 milliliters of 3 molar solution. Okay, so I'm simply going to use my C1V1 equals C2V2, C1 times V1 equals C2V2, and I need to plug in my information. In this case, my stock solution, or my C1, is 6.0 molar, and I don't know how much of the stock solution I want to use. That's what I'm trying to determine, so I'm going to leave that as V1. My C2, or my final concentration, has been given as 3.0 molar, and I'd like to make 500 milliliters of it. I don't need to worry about what the units are here, as long as all my units cancel. So my concentration can be in molarity, it could be in weight volume percent, it could be in any other units I'd like, as long as they cancel if I'm plugging 2 units of concentration in. Same thing with the volume. Because I'm in milliliters here, my answer will be given back to me in milliliters, which is fine with me. Now I just need to solve for my variable, or isolate V1. I do that by dividing both sides by 6 molar, and I do a little bit of math, and I find out that the volume 1, or the volume of stock solution that I need to use, is 250 milliliters. In other words, if I take that 6 molar stock solution, I measure out 250 milliliters into something like a beaker or a volumetric flask, and then I add water until I have 500 milliliters total, my final concentration will be 3.0 molar. So C1V1 equals C2V2 is a really useful calculation that's used frequently in laboratories and medical clinics around the country.